So hello, welcome to this month's instalment of the IMechE Postgraduate Tribology webinar series, Who, What, Why and Where. These webinars provide a welcoming and supportive platform to facilitate the interaction between researchers from across the UK, both within industry and academia. And in the past, we've had presentations that have typically covered topics ranging from rail to bearing, space applications, and biotribology. And this webinar series has been running since September 2023, and it's been great to see the number of people registering and attending steadily increase over the last 6 months. So in keeping with our normal format, this 1-hour webinar will consist of 2 presentations, both lasting approximately 20 minutes, with opportunity for questions after each. And today's talks will both focus on research related to rolling contact. So we've got 2 speakers today. We've got Dr. Rui Dai from the University of Sheffield, and we've got Daniel Powers from the University of Southampton. So Rui is going to be talking first today, and Rui is a research assistant within the mechanical engineering department at the University of Sheffield, and his talk is titled Damage Characterization and FE Modelling of Subsurface Rolling Contact Fatigue in Wind Turbine Gearbox Bearings. So yeah, with that said, I'll hand over to Rui now, so he can begin his talk and pick up after for questions and answers. Thank you.
Okay, thank you, Karen. So my name is Ray, and I'm going to talk to you guys about my research about the damage characterization and FE modeling of the subsurface rolling contact fatigue in wind turbine gearbox bearings. And at the beginning of my presentation today, I'm going to talk about my research background here. And then I got some real pictures from the real field bearing. And I'm going to show you guys these pictures about the subsurface rolling contact fatigue. And in the end, I'm going to introduce my FE modeling of the subsurface rolling contact fatigue. And I use the continuum damage mechanics, which is called a CDM method in my FE modeling. Okay, here's the research background. If we look at the pictures in the top right, it is the structure of the wind turbine drivetrain. And for all the drivetrain failures, the gearbox failures takes about like 10% of overall drivetrain failures. But in this gearbox failures, the bearing problems is a big issue here, and it takes about 76% of overall gearbox failures. And that is the reason why my research is on the gearbox bearings, as you can see here. And there are 2 bearings I investigated in my project. The first one is the upwind planetary bearing, which has been marked by these black circles here. And the second one is the downwind planetary bearing. They all come from the V80 2 megawatts wind turbine gearbox, and the manufacturer want us to find out what's the reason for the premature failure of these bearings. And based on our investigations here, we have found that the subsurface rolling contact fatigue, the subsurface RCF, is the very important to this premature failure of the bearing. And we also found that there are 2 reasons for the rolling contact fatigue here. The first one is the stress concentration caused by these subsurface inclusions. And the second one is related to the loading applied on the bearing. So sometimes the overloading cases may accelerate the subsurface rolling contact fatigue and cause the premature failure of the bearing. Okay, let's look at the microstructure damage characterization first. And I left-hand side is the linear raceway of the bearing is fixed with the planetary carrier. So when you put a torque on the bearing raceway, so the loading zone is fixed as shown by the picture B here. So the loading zone is fixed. So in the real bearing here, so you can see some certain area on the surface is damaged, but a lot everywhere is damaged. It's just fixed on a certain area. And I'm going to look at the subsurface damage in the circumferential direction and axial direction to see the difference between these two sections. And before we use the optical microscope and SEM to do the observation, these samples should be polished and etched as shown by the picture here. Okay, here's the pictures of some rolling contact fatigue damage here. And I think the first damage stage is the damage caused by the subsurface inclusions. In most subsurface areas of the bearing, so the most inclusions are undamaged, as shown by the figure A and the figure B here. They are undamaged inclusions. But because we have the heat treatment and loading on the bearing, so sometimes we got some boundary separation between the steel matrix and the inclusion, and sometimes the inclusion itself may have some internal cracks, as shown by picture E and picture F here. They are internal cracked inclusions. So the stress concentration level of these inclusions will be higher because they are already damaged by this boundary separation or internal cracking. Then we got some subsurface rolling contact fatigue cracks propagate from the tips of the inclusions. These are so-called butterfly damage. And sometimes we can also observe some white edging areas around these butterfly cracks. These white edging areas is a change of the steel structure from magnetite to ferrite, and it makes the material becomes hardened and much more brittle, and it reduces the toughness of the structure and accelerate the crack propagation here. And the second stage of the rolling contact fatigue is related to the crack propagation. So when we have the fatigue cracks propagate from these small inclusions, they may connect with each other and form into very long subsurface crack networks, as shown by picture A and picture B here. They are all subsurface cracks. And if these subsurface cracks propagate to the surface, and it will cause the spawning on the surface, and it accelerates the failure of the bearing, as shown by the figure C and figures D over there. And when the surface is already damaged, it will cause very high stress concentration on the surface, and maybe sometimes because the surface is damaged, we may have some impact loading from the rollers. So these kind of loadings may cause the secondary cracks, as shown by the pictures on the right-hand side. These secondary cracks are typically very long because the loading is very high, and it accelerates the failure of the bearings and accelerates the spawning on the surface. And also, we can also observe some white edging areas of these cracks. And as you can see on the left-hand side is a very long white edging crack, WEC, observed in the subsurface area. And you can see many WEAs can be observed near the cracks. And at the moment, we still don't know which one comes first, which one forms first. The WEA comes first or the cracks first. we still don't know. But in this case, I think the crack may initiate first, because if we look at this picture in detail, we can see the white etching area in a very deep area. It's about like 4 millimeters below the surface. And I think without the influence of cracks, the white etching area will not be produced in such deep area, because the effect of loading on the surface may only like affect the region like 1 millimeters below the surface, but this one is about 4 millimeters, so it must be the effect of cracks. So in this case, I believe the cracks initiate first, and because of the formation of cracks, there may be some very complicated reactions between this crack surface, maybe squeezing and friction and heating between these crack surfaces. And then we have the dissolution of cementite and the redistribution of carbon and chromium elements. Then we have the white etching area in this along these cracks, and that is the so-called WEC in this specific bearing. So here's the quick conclusion here. And the stage 1, we have butterflies, and the cracks may propagate and connect with each other. So that is the subsurface crack network. Then we may have some WEA and WEC, which accelerate the crack propagation. And the final stage is the surface spawning, or the premature failure of the bearing. Then I'm going to introduce my FE part. It's a two-dimensional FE modeling of the subsurface rolling contact fatigue due to inclusions. In my FE modeling, I simplified the contact between the roller and the raceway into this rectangular model here. And as you can see, I did not have the rollers in this model. And I use the Kurt's contact pressure and the surface traction pressure to simulate the movement of the rollers on the raceway. And these pressures will move cyclically from the left to the right, which simulates the cyclical rolling movement of the rollers on the raceway. And also I defined an inclusion, which is a MNS inclusion at the depth of 0.398 millimeters. This area is the area that maximum shear stress occurs with the contact pressure of 2 gigapascal, which is the rated pressure on the bearing. So in the end, I use the damage model to define the fatigue behavior of the material. This damage model comes from a published paper in 1999. Okay, let's look at the flowchart of the FE modeling with the CDM method. And at first, I defined the plastic deformation in my modeling because we have the stress concentration due to inclusions, so it may have some plastic formation in the subsurface area around these inclusions. And when the yielding happens, I also consider the Boschinger effect of the material. Then I calculate the back stress, and I will update my stress based on the kinematic hardening model here. And as you can see in the right circle here, this is the equation I used to update the damage parameter D in the CDM damage model. And in this fatigue model, this D value is related to the amplitude and mean value of the alternating orthogonal shear stress. Okay, and the reason why I use this amplitude and the mean value of the stress is based on the Goodman fatigue theory, because it believes the fatigue behavior of material is related to the stress level and the mean stress of the overall loading. So That is why I use these two stresses here to calculate the damage value. And sigma r and m here are material constants which can be determined from the SN curve of the material. And in the green circle here, this is the constitutive equation of the material. And when the damage happens, the stiffness of the material is reduced. Then I will update all the stress based on the constitutive equation here. Okay, let's look at the results of my FE modeling. At first, I'm going to figure out the effect of the inclusions with different damage types based on the optical microscope observation. And we have found that some inclusions are undamaged and some has the boundary separation and some has the internal cracks. So I compared the effect of these three kind of damages of the inclusions. In these three FE models, the maximum Hertz contact pressure is fixed, and the contact cycle simulated is 20 million, which is also fixed, and the traction coefficient applied is 0.1. The traction pressure is caused by the friction between the roller and the raceway, so this value is linked with the lubricating condition. So when the lubricating is good, so the coefficient is small. In this case, all the in these three models, the value is fixed as 0.1 here. And if we look at the results, and we can find it doesn't have any damages at the tips of the inclusion in this undamaged inclusion modeling, but when it has the boundary separation between the inclusion and the steel matrix, it has the fatigue crack here. And it also has a fatigue crack here when the inclusion is internally cracked. So, and then if we compare this boundary separated inclusion and the internally cracked inclusion, we can find out that the internally cracked inclusion causes the longer fatigue crack than the boundary separated inclusion. That means internal cracking of the inclusion is more harmful in the subsurface rolling contact fatigue. And then I'm going to investigate the effect of surface traction pressure. So I change this surface traction coefficient from 0.01 to 0.1 to see the difference between the surface traction pressure, and all other values are fixed, such as the maximum contact pressure and the contact cycle simulated. And based on the modeling results here, I think the fatigue crack length increases with the surface traction pressure, and especially when the traction coefficient exceeds 0.05. So that means when the lubricating conditions becomes worse, and it will accelerate the fatigue and accelerate the damage of the bearing. So the bearing with better lubricating conditions will have a longer fatigue life. In the end, I'm going to study the effect of the loading variation on the rolling contact fatigue. And in this case, the loading is not a fixed value, but it changed from 0.92 to 2.84 gigapascal here. All these values come from the calculations of the wind turbine manufacturing standard. And if I look at this picture here, and in this case, the loading only changed once from 0.9 to 2.84. But in this case here, I caught two loading groups because it changed twice from smaller value to big value, then change from smaller value to big value again. And we can see the difference. The fatigue cracks becomes longer than it changed once. Then if we change it 4 times, then I caught 4 loading groups. So it changed 4 times from the smaller value to a big value, and then we compare these results together, and we find that when it changed 4 times, it had 4 loading groups here. The crack length is longer than the 2 loading groups and the 1 loading group here. So the loading sequence of the different loading amplitudes does affect the initiation and the propagation of the fatigue cracks. And the more frequently the high stress magnitude occurs, the longer the fatigue crack will be. This change, as I said, this change of loadings may come from the change of the wind speed or the other conditions such as the braking or the grade loss that may all cause the change of the loading on the bearing. To validate the effectiveness of the FE modeling, I compared the modeling results with the twin discs test results come from the published paper of the University of Southampton. And it can be found that my modeling results is very similar to the real butterfly damage in the twin disc test. I have 3 comparisons here, and all the results I think they are very good. But when I'm going to use this FE modeling to simulate the real butterfly from the real field bearing, I think the result is not satisfactory, because when I compare the propagation direction and the length of the butterflies here, they have very large difference with the real butterflies in the field bearing. So I think this may have some problem here. First, the effect of the difference between the assumed and the actual loading conditions on the raceway, because we can't simulate the real loading conditions on the bearing, so that may cause the difference. That's the first reason here. And the second reason is about the geometry of the inclusions in the modeling here. It's just a 2-dimensional modeling, but in the real case, the inclusion is like 3-dimensional, and it may have some irregular boundaries, so that is not considered in the modeling. And the last one is the damage of is the already damaged contact surface of the raceway, because the raceway surface is already damaged, and it may cause some stress concentration or change of pressure on the surface. So that may also cause the difference between the modeling and the real butterfly damage from the bearing. Okay, and that's the end of my presentation. And do you have any questions about it?
Perfect. Thank you very much, Rui. All really interesting.
Yeah.
Yes, if you've got any questions for Rui, please just put them in the question box, which should be on the right-hand side of your screen. We'll make sure to get those to Rui. So we've had a couple come through already, and one of which is, what software have you used to conduct the simulations in your work? Did you catch that, Rui?
Sorry, I didn't hear you. Sorry.
All right, we just had one question come through, which is what software did you use to conduct your simulations as part of this?
It's based on the Abacus, and for the modeling of the material, the modeling of the fatigue behavior of material, I use the subroutine of Abacus to, it's just a program here, and to define the properties and update my stress here. So, yeah.
Perfect. Thank you. Also, another question is, why did you consider the Bauschinger effect in FE modeling, or why is it important to consider the Bauschinger effect?
Okay, in the Bauschinger effect, it says when it has tension and compression, and for the material, so the it may have a kinematic hardening here. So that is the reason why I consider the compression and the tension force here, because if we imagine when the roller is on the left hand side of the inclusion, and then the stress around the inclusion is like tensile, but when the roller just moves above the inclusion, the overall stress becomes compressive. So it's a very complex change of the subsurface stresses from tensile to compressive, and then from compressive to tensile again. So it's a very complicated change of stress here, and because of the stress concentration, it may also have the plastic deformation. So that is the reason why I consider the Bollinger effect here. So.
Okay, perfect. Thank you.
Okay.
I just had another question come through. Is I guess, can your methodology or workflow be replicated on other failures? And do you have any future plans?
Okay, so I think it's just suitable for the for the cylinder rotors on the bearing, because I can simplify this one. Because if we have a cylinder rotor and a cylinder raceway, I can simplify it into a two-dimensional. But if we got other bearings, I don't think so. And the other one is the definition of the stress. It can only move cyclically from the left to the right, to the right. But if we have the oscillation on the surface, I don't think this model can tell you what will be the be a result when you have the oscillation on the surface. So, yeah.
Okay, thank you. And how do you go about modeling 20 million cycles in FE? How does that look?
All right, it's a good question. The 20 million cycles is a very large number, and I can't simulate from the from 1 to 20 million. So that's impossible. So what I did here is I defined the so-called jumping loading cycles. So for example, if I only have 400 jumping loading cycles here, and I only need to simulate this loading cycles, but in this loading cycle, in this jumping loading cycles, it may contains like 50,000 cycles here. So I only need to do the simulation of 400 cycles, but in one cycle, it's just like a loading block, and so.
Okay, cool.
Yeah.
And just had another question come through. So it's typical to predict rolling element bearing life using the L10 type model and the applicable loads. Do the types of failure observed in wind turbines deviate from the standard bearing life models in some way? I.e., are there some specific conditions within gearboxes which make the standard life models inaccurate?
It quite depends on the quality of the bearing, I think. For my case, this one is a very old bearing, and it's don't have very good quality because it has very even many inclusion in the subsurface area. So yeah, well, so that means it's very particular for it's a specific case for each bearing, so we can't say we can use this model to simulate all the bearings and given all the fatigue lives of the bearing.
Perfect. Thank you. So please do keep your questions coming for Rui, and if we do have some more time at the end, we'll try to get those answered. But I think in the interest of time, we'll move on to Daniel's talk. So thanks again very much, Rui. Really interesting talk. So next we've got Daniel Powers from the University of Southampton. And Daniel's a PhD student working within the National Centre for Advanced Tribology, which is the NCATS group for short. And his presentation today is titled Experimental Investigations in Electrical Discharges Through Rolling Contacts. Cool. So I'll hand over to you now, Daniel.
Cool. Right, hopefully that's all come up. Let's hide that. Right, hello. Yeah, as I said, my name's Dan. I'm here to talk about just some of the results that I've been getting from some ongoing experiments as part of my PhD, looking at electrical discharges through rolling contacts. So what I want to do with this presentation, I'm just going to quickly introduce the background to the project, some of the aims and its theory, just because there's a little bit of electrical theory I want to bring to the forefront to help clarify some of the results. And then I'm going to show off those results and try and explain how I'm interpreting them and what conclusions I'm drawing and where the project's going to go in the future. So just to start off with, I've found a quote from a book that was recently recommended by one of my supervisors. It's not profound, but it's sort of appropriate to what this presentation is all about. And it goes, the erratic nature of insulation is most pronounced in mineral oil when used alone. So I'd just like everyone to keep that in mind at the back of your mind while some of the later things come up in this presentation. A little bit of background to where this study comes from. Similar to Rui's wind turbines, it's electric motors have stray currents that are induced in their housing, and then they pass through the bearings, and those stray currents can cause the bearings to fail faster than ones that are uncharged. So if it's in a regular wheel axle. And a lot of research has been done into this phenomenon for quite a few years now, but most literature that I've found and have read through focuses on testing full complement bearings with bearing races and rolling elements, and there's not so much investigation into how the electric current passes in a transient nature, and also the amount of focus on the tribological scenario isn't that great. So what I wanted to do with my research is base it on a single rolling contact with which I can investigate the mechanisms of electrical discharges across a single surface pair, which I think is a little bit more controllable. So what I'm going to be aiming to do with this project is to generate controlled electrical current through a single rolling contact and establish a method to record its behaviour, and then vary the electrical and tribological parameters and scenario across this contact, and record the effect of this variation on their current passage. And then I'm going to evaluate what get out of that, how these parameters are linked to resultant electrical signals, and whether that matches like some assumptions that we make about the contact. So just to quickly reintroduce or bring to the forefront of your mind some of the appropriate tribological theory. Hopefully everyone's heard of the lambda ratio, which defines your degree of separation of asperities and the lubrication regime. But in an electrical sense, as this changes, the oil film can be represented as either a resistor, a combination of resistor and capacitor, or at full lubrication, just a resistor, not a resistor, just as a capacitive element. And classically, we use the Hertzian area and the film thickness to determine the capacitance at full lubrication. But as the lambda ratio decreases, that approximation sort of breaks down, and that's not been investigated quite as much. When the charge across the contacts exceeds the breakdown strength of the oil, you get the spark discharge through the oil, allowing the voltage to pass through the current contact, which can, in some cases, if the scenario is severe enough, cause microscopic damage to the bearing raceway, which is what causes it to fail faster. And there's been investigations made into this area, and they've proposed thresholds, current densities, power densities, which will determine whether your current will produce a significant amount of damage and cause it to fail before classical rolling contact fatigue. So this is the apparatus that we've got at Southampton. I know Rui mentioned it about the twin disc. It's a T74 twin rolling machine by Phoenix Tribology. We have 2 rolling samples. In my case, it's 1 crowned and 1 flat. One's twice the diameter of the other. And we spin them in, for this test, PaO8 oil. It's just base oil, which creates a nice lubricated contact. And the T74, with these samples, we can produce a range of film thicknesses, a range of contact areas, contact pressures, which gives us enough scope to test all the lubrication regimes and give us a nice variation in electrical behavior. So with that, we hook up a DC supply with a regulating resistor in series to regulate the amount of current that we pass through the contact. And for the test that 2 tests that I'm about to present the results for, I just run a sample pair in, and then once that happens, we apply voltages between 1 and 20 volts with different resistor values swapped in and out to generate the discharges across, in this case, a fully lubricated contact, very, very high lambda ratio. And we use a picoscope, which is basically a very fancy oscilloscope connected across the contact and the resistor to measure transient voltage signals, and what I'm going to refer to them from now on as waveforms. When the sample's running stably, I've ramped the voltage in 1 volt increments from 1 to 20, and at each resistor voltage combination, I've taken a bank of waveforms from which I can sort of look at what the behavior of the electric current for that combination. But what does this actually look like? This is just a raw image of what comes out of the picoscope software. This is just one example of one of the waveforms. This thing takes hundreds of these sort of waveforms, so I've just brought this one up as an example to demonstrate all the different features. The red line is the charge across the contact, the blue is the one across the resistor. So each waveform is a combination of capacitive charging, which is shown by the sort of large spikes in on the line, which I've called a capacitive discharge event, or CDE. Each event has its own individual discharge voltage, which, again, remember that quote, due to the erratic nature of insulation. So the breakdown voltage is a statistical value of what you're actually going to get. So for the first test, I ran it at 60 degrees, and I only had the 30 kilo ohm and 12 ohm resistors, so one very, very low current, one very, very high current scenario. And in this case, I didn't manage to, because this was used on an older electrical setup, so I didn't manage to record the voltage across the resistor itself. This is just across the contact. So the immediately observable things, or aspects of the waveforms, the charge rate for high current, for the high current scenario, is much, much higher. That's why the spikes are almost vertical. And it seems like between them there's a very, very small discharge current between them, but that's just the prevalence of the internal resistance of the circuit. So for test 2, I was able to refine it a little bit, and ran it at the same scenario, apart from increasing the temperature up to 80 degrees, and used resistors that were slightly closer in value, just to evaluate, to sort of show the transition between these two scenarios a little bit better. For this time, I recorded the waveforms from 2 volts to 16 volts because I didn't think it was necessary to have quite as much detail for 1 volt steps. In this case, I've exhibited only the ones where the 4 volts was applied to show the difference in current, the difference that the current effect has. And you can see that as the resistor value decreases, the current increases, the cleanliness of the signal decreases. You get the increase in internal resistance, and the sort of insulating properties of the oil become much more difficult to establish for some reason. So that's why I've sort of described it as sporadic charging for the high current scenario. So what can I do with these waveforms? To start off with, I've just extracted individual discharge events and then stacked them together. So the first one was for the 30 kilo ohm resistor from test 1. I just put ones under the same voltage just to check that the charge rate was similar, and it shows that they are, which means that the film thickness is constant, or well, as consistent as it needs to be for this sort of test. And then for the second graph shows 5 discharges that I've sort of plucked out at a maximum value from like quite a long waveform. This is me just picking out the highest one I could find, but as you can see, at higher applied voltages, the maximum discharge voltage actually doesn't reach what that applied voltage is, because it's breaking down around the breakdown voltage. And you can see that the charge rate varies with voltage as well. So with MATLAB, you can also count the peaks across multiple waveforms. So in this case, I've counted not only the amount of discharges for 10 times 10 millisecond waveforms, I've also recorded the value of each discharge voltage, and then seen what the distribution is. And it follows a rough Weibull distribution. It's a little bit spiky because it's not that many, but with more tests, I can smooth out the line a little bit. But what it also shows is a sort of a significant amount of sub 1 volt discharges, which I think might be to do with the film thickness or the insulation of the oil not re-establishing itself, or just by vibration causing little changes in the voltage across the contact. But it does show that with increased applied voltage, the average value of discharge increases. So the clincher that I'm currently fighting with is trying to explain why there are gaps between some discharge events, especially in the low resistance scenario. So this case is the 30 kilo ohm resistor. That's a really low current, and I've been able to apply 16 volts. That's really high, far beyond what the breakdown voltage was. But you can see that the charging is still clean. There are some gaps, but they're not quite as dramatic as the when I had the 12 or the 150 ohm resistor. And yeah, this waveform here is I've cut out only 3 milliseconds, but it's easy to count the amount of discharges. It's easy to park that in MATLAB and say, count the amount of peaks, please, and it'll give you a clean one. But then when you swap in the 150 ohm resistor, leaving it in exactly the same tribological scenario, basically I've left the rig running, turned off the power supply, pulled out the resistor, swapped in the other resistor, and applied the power again. That's how quick it was done. There's only 2 major discharges and 2 extra sort of slightly more minor ones recorded in the same 3 millisecond period. Even though the charge rate's significantly higher, so if this if it wasn't doing all this sort of continuous current scenario, you'd be counting hundreds or if not thousands of discharges if it kept the insulating property. But in this case, we get individual discharges and then continuous current for a significant amount of time until something happens. With this case, I'm still trying to figure out why using the low value resistors doesn't allow sort of re-establishment of insulating properties, even though the spinning discs are continuously bringing in fresh oil. And if you think about them rotating against each other, any metallic bridges will break just through rotation. If you want me to fully explain, get back to me in a month, because I'm currently running around people who know more than me, trying to work out roughly what may or may not be going on. So with all that like entertainment out of the way, what conclusions have I drawn? Well, at the very least, I can use the T-flame board to create a good rolling contact with controlled electrical stress for the evaluation of individual discharges. The charge rate's consistent for each discharge event, and it varies as expected for applied voltage and resistance. The distribution of what discharges, the discharge values, follows a Weibull distribution. What that extra low voltage spike represents, I'm not sure. And with the high current scenario, it prevents, to a degree, the re-establishment of the insulating field of the oil. So in the future, I'm going to be extending the study with even more resistor values, trying to focus in on the combination of capacitance and lambda ratio, and then a little bit of simple modeling of the contact in ANSYS to verify some of our capacitance assumptions, because as I mentioned, classically we assume that the contact area is the capacitor area, but that's sort of being challenged here. And then keep investigating the influence of high currents, maybe extend it outside of a rolling contact, just have 2 plates, and then just to simplify it and see what's happening there. And then a long time down the road, slightly longer tests to combine these electrical signals and the tribological conditions to resultant damage that happens when you run this for much, much longer than this test was run. So I'd like to finish up with just a quick list of references for some of the figures that I had in earlier slides, and I will ask for any questions.
Perfect. Thank you very much, Daniel. Really enjoyed your quote and how you used it. So yeah, if you've got any questions for Dan, please send them through on the right hand side of your screen, the question section. So we had one come through already. So could you please tell us more about your theoretical models developed for the experiment you've conducted? Was it fully analytical, or did it have elements of MATLAB Simulink used?
So they're still being built. So what I've been assuming for the tests so far is based on what people have presented in literature. I've showed that diagram of the different tribological scenarios and how they relate to electrical signals. It's mainly based on that, and there are some other ones I could pull up from other pieces of literature where they sort of vary what the combination of resistance and capacitance is. They've not really produced that or put out that many numbers, which is what I'm trying to get out of this project, is sort of like put some numbers into places. With actual so the model so far is purely analytical. It's based on just calculations, but I've started going into using ANSYS EDT to just create. Start off with just a simple curved surface, and then also modeling a slight bit of roughness on it as well. So from that's I'm going to hopefully be getting sort of equipotential lines and different capacitances.
Awesome. Thank you. So just got another question for you. How do you make sure that the signals that you record are purely due to the separation of the contacts and no short circuits are created anywhere?
So on the T74, we've got two sort of brushes that connect up to the samples. There's insulation between, so we've got some rubber and plastic parts that protect the rest of the rig from the electrical connection. So there's a little rubber thing that goes around one of the oil inlet tubes that protects it from spring that sort of holds the contacts onto the spinning disc. And before each test, hook it up and sort of lift the load arm just to check that the voltage sort of swaps. So when it's together, it's fully current continuously passes and all the voltage gets taken across the resistor. And then when you lift it up, the circuit gets broken and all the voltage gets shown across the contacts, and that's how we make sure that the contact is doing what it's supposed to do.
Okay, got you. Yeah. And do you have any plans to consider AC current in the future?
Yes. Actually, something my supervisor suggested. Originally, it was supposed to be AC. Well, that was the idea at the start, but to verify things, we've been using DC. But in the future, we've got quite a big AC source that we'll be doing, finding the effective frequency as well, finding the effective, because in electrical motors, it's all AC and the frequency of discharge is quite high. So yeah, we'll be using AC to see what the difference does.
Yeah, perfect. So just had a question come through. So electrical discharge is a major problem in electrical motors. Do you intend to bring insulated bearings to see the benefits?
So I've read plenty about like mitigation techniques. You can use insulated bearings to protect your motors. Some people have designed shaft bonding devices which sort of direct current around the bearing straight onto the shaft. And while I'm very happy that these exist for industry to solve it. I just want to, with this project, I wanted to sort of look more at the theory and just understand why / how these electrical discharges occur.
Perfect, thank you. So with that, I think we'll start to bring things to a close. So thanks again to both our speakers today. Really interesting work and super excited to see where it goes in the future. We're really keen to continue the webinar series in the future. So if you are interested in giving a talk, please do get in contact. By email is probably the best way to do so. And you can do that via the address membernetworks@IMechE.org. So just to repeat that, that's membernetworks@IMechE.org. Also, just a quick notice that the deadline for the tribology bronze medal applications are fast approaching. So the tribology bronze medal is awarded typically to one person, but last year to two. And it recognises high achievement and a commitment to tribology at an early career stage. So the deadline for those applications is the 31st of May. So yeah, that concludes today's webinar. Thank you very much, and hope you all have a nice weekend.